Before you drift away, find a place to lie down. Close your eyes, let your body sink into the surface beneath you, and breathe slowly. Allow the quiet of this moment to settle around you as you listen to the unfolding story of Earth's climate, a story written over millions of years. Subscribe to explore a new documentary each evening and tell us where you're listening from. Quick question: what time is it where you are? Hold on, I've got one final question before we start. Could Earth's climate suddenly shift toward another ice age within our lifetime? This question leads us through time, across frozen landscapes, and into the deep records held by ice, rock, and ocean. Long before humans walked the Earth, the planet experienced vast cycles of cooling and warming. Ice ages are periods when large areas of the surface are covered with thick ice sheets. These events shaped continents, oceans, and life itself. The earliest known ice age, the Huronian, occurred about 2.4 to 2.1 billion years ago. During this time, oxygen began to accumulate in the atmosphere, a period called the Great Oxidation Event. Ice spread across much of the planet, creating glaciers that stretched across continents. Scientists reconstruct these ancient climates using geological formations, glacial deposits, and isotopic evidence from rocks. The Huronian glaciations were profound, lasting hundreds of millions of years in stages, with repeated expansions and contractions of ice. Hundreds of millions of years later, the Cryogenian period, approximately 720 to 635 million years ago, brought an even more extreme cooling. During this period, some scientists believe that ice may have reached near the equator, an event often called snowball Earth. Layers of glacial sediment embedded in tropical latitudes suggest that ice sheets covered nearly the entire planet. Volcanic activity, continental drift, and atmospheric composition contributed to these changes. Carbon dioxide levels, which influence global temperatures, were unusually low. Evidence from carbonate rocks and glacial striations shows that temperatures could have dropped to levels that made most life struggle to survive. Yet life endured in oceans, protected from freezing by salty, dense water. Later, the Andean-Saharan Ice Age, about 450 to 420 million years ago, marked a time when glaciers spread over regions that now include parts of Africa and South America. Fossil records show that plants and early animals adapted to fluctuating conditions. Glacial deposits and tillites preserved in rocks provide evidence of ice coverage, and these formations reveal information about ice movement and the climate at the time. Each ice age leaves behind unique markers, telling the story of how Earth's systems respond to changing energy from the sun and shifting continents. The most recent and familiar series of ice ages began about 2.58 million years ago in the Quaternary period. During this time, large ice sheets grew over North America, Northern Europe, and Asia. These periods of glaciation alternated with warmer interglacial periods, creating cycles of advance and retreat. The evidence comes from a combination of ice, cores, sediment layers, and fossils. Ice cores drilled from Greenland and Antarctica contain bubbles of ancient air, preserving the chemical composition of past atmospheres. By measuring isotopes of oxygen and hydrogen in these cores, scientists determined past temperatures. Sediment cores from ocean floors show the accumulation of ice-rafted debris, offering further clues to glacial activity. The timing of glacial cycles in the Quaternary is closely linked to changes in Earth's orbit. Variations in eccentricity, axial tilt, and precession alter the distribution of sunlight reaching the planet. These Milankovitch cycles influence the growth and melting of ice sheets over tens of thousands of years. Ice ages are not sudden events, but unfold over millennia, with periods of gradual cooling, followed by more rapid melting. The accumulation of ice changes the landscape, carving valleys, forming lakes, and redistributing sediments. Glacial erosion creates U-shaped valleys and fjords, while moraines and drumlines mark former ice margins. These physical traces persist long after the ice retreats, recording the movement and strength of glaciers. During glacial periods, sea levels dropped as water became locked in ice. Coastal areas that are now submerged were exposed, allowing species to migrate and humans to traverse land bridges. In the last glacial maximum, around 20,000 years ago, ice sheets covered much of North America and northern Europe. Sea levels were more than 100 meters lower than today, and large rivers carved channels across what is now the continental shelf. The cold, dry air influenced wind patterns and precipitation, shaping ecosystems and biomes across continents. Fossil pollen and charcoal layers revealed changes in vegetation and fire frequency, reflecting climate stress on ecosystems. Ice ages are not only about ice and cold, they are about the interactions between Earth's atmosphere, oceans, and land. Volcanic eruptions influence climate by releasing aerosols and gases that reflect sunlight, temporarily cooling the planet. Ocean currents redistribute heat, affecting temperature and rainfall patterns far from the source of glaciation. Atmospheric carbon dioxide and methane levels act as regulators, amplifying or mitigating cooling trends. Studying these complex interactions helps scientists understand the potential for future climate shifts. As we look at the patterns of the past, we see that ice ages are part of a rhythm that has repeated over billions of years. Each ice age leaves a detailed record in the rocks beneath our feet, in the cores drilled from glaciers, and in the sediment layers of the oceans. They are records of Earth's natural response to changes in energy balance, the position of continents, and the composition of the atmosphere. While the timing and intensity vary, the cycle of cooling and warming is a constant in the planet's history, providing context for understanding the present and the potential for abrupt changes in climate. The study of past ice ages not only explains how the planet has changed, but also guides scientists in predicting future trends. By reading the markers left in ice and stone, we learn the sensitivity of Earth's systems and the potential consequences of disruptions to the balance of energy and gases that regulate the climate. In this understanding, we begin to grasp the mechanisms that could, in theory, bring about another period of extreme cooling, even in a world now influenced by human activity. The last time Earth was at its coldest in recent history is known as the last glacial maximum. This period, around 20,000 years ago, marked the peak of the most recent ice age. Vast ice sheets stretched across continents, shaping the land and climate in ways that are still visible today. In North America, the Laurentide ice sheet covered much of Canada and extended into the northern United States. In Europe, ice spread over Scandinavia and large portions of the British Isles. Smaller glaciers moved across the Alps, the Pyrenees, and mountain ranges in Asia. These ice sheets were massive, sometimes exceeding 3 kilometers in thickness, pressing down on the crust beneath and altering the shape of the land. Their weight caused the Earth's surface to sink in some areas, while raising land elsewhere as ice melted. Scientists study the remains of these ice sheets through glacial deposits, moraines, and the scratches they left on rocks, known as striations. Each mark tells the story of ice advancing and retreating over thousands of years. Sea levels during this time were much lower than today. Water was locked in ice, reducing global sea levels by more than 100 meters. Coastlines that are now submerged were exposed, connecting islands and continents. The Bering Land Bridge, for example, allowed humans and animals to move between Asia and North America. Exposed continental shelves provided habitats for animals and plants and allowed migrations that would not have been possible under today's sea levels. Ocean currents shifted with the changing distribution of water, influencing temperature and precipitation patterns. Scientists reconstruct these patterns by studying sediment cores from the ocean floor. Layers of sand, clay, and organic material reveal changes in ocean circulation and sedimentation. Chemical analysis of these sediments, particularly the ratios of oxygen isotopes, provides insight into temperature fluctuations and ice volume. Atmospheric composition also played a critical role during the last glacial maximum. Carbon dioxide levels were lower than pre-industrial times, averaging around 180 to 200 parts per million, compared to about 280 parts per million before the Industrial Revolution. Methane concentrations were similarly reduced. These lower levels contributed to cooling as greenhouse gases trap heat in the atmosphere. Ice cores from Greenland and Antarctica preserve tiny bubbles of ancient air, allowing scientists to measure the exact composition of the atmosphere tens of thousands of years ago. By analyzing the isotopic ratios of oxygen and hydrogen in ice, researchers determine past temperatures and precipitation patterns. Each ice layer represents a year or season, providing a detailed record of the climate at the time. The thickness and density of layers reveal periods of heavy snowfall or dry conditions, giving a sense of the rhythm of the glacial environment. Flora and fauna adapted to the cold in remarkable ways. In Europe, large herbivores such as mammoths, reindeer, and steppe bison roamed the tundra and grasslands that stretched south of the ice sheets. Carnivores, including wolves and large cats, followed these herds, hunting across open landscapes. Forests retreated to refuges in southern Europe, where oaks, pines, and other trees survived in pockets of more temperate climate. In North America, similar patterns occurred. Coniferous forests shrank southward, and tundra expanded in the north. Plants and animals evolved or migrated in response to the advancing ice and changing climate. Pollen preserved in lake sediments helps scientists reconstruct these past ecosystems. Each pollen grain provides a record of what plants were growing and where, revealing how vegetation shifted in response to temperature changes. Humans also adapted to these harsh conditions. Hunter-gatherer societies developed tools and strategies to survive in cold environments. Evidence from archaeological sites shows the use of specialized weapons for hunting large animals. Clothing made from animal skins and furs provided insulation. Humans created shelters that protected them from wind and snow, sometimes using mammoth bones to construct frames covered with hides. Coastal and riverine areas were important sources of food, offering fish, shellfish, and plant resources. Migration was common as groups moved to follow the availability of food and more favorable climates. Artifacts, including stone tools, carvings, and cave paintings, offer insight into how humans understood and responded to their environment. These adaptations were crucial for survival during a time when cold and ice shaped every aspect of life. The interaction between ice sheets, climate, and life forms can be traced through multiple scientific methods. Sediment cores from lakes and oceans reveal the accumulation of organic material and glacial debris. Isotopic analysis of oxygen in these sediments indicates temperature shifts and ice volume changes. Ice cores provide direct evidence of atmospheric gases and climate variability over thousands of years. Fossilized remains of animals and plants indicate migration patterns and ecological shifts. Together, these data create a detailed picture of the last glacial maximum, showing not only the extent of ice, but also how ecosystems and human populations responded. Each layer of ice, each deposit of sediment, tells a story of resilience and adaptation in a world dominated by cold. Glaciers sculpted the land through erosion and deposition. As ice advanced, it ground rock surfaces into fine sediment, carrying debris across continents. Moraines, formed from accumulated rocks and soil at the edges of glaciers, mark the limits of ice sheets. Drumlins, small hills shaped by moving ice, provide insight into ice flow direction and velocity. Glacial lakes formed where meltwater collected behind ice dams, some of which drained catastrophically, reshaping river valleys. The landscape bears the fingerprints of ice age processes, visible today in fjords, valleys, and plains. Geologists use these features to map the maximum reach of ice and understand the dynamics of glacial movement. Satellite imagery and aerial surveys allow precise measurement of glacial landforms, revealing patterns invisible at ground level. Temperature variations were not uniform across the globe. While ice sheets dominated the northern hemisphere, some areas experienced only moderate cooling. Tropical regions retained forested environments, though rainfall patterns shifted. Mountain regions in the tropics hosted glaciers at high altitudes. In the southern hemisphere, ice covered parts of the Andes and other highlands, while much of Africa and Australia experienced drier, cooler conditions. Ocean temperatures also decreased, affecting marine life and nutrient distribution. Coral reefs show evidence of stress during this period, and plankton fossils record changes in ocean chemistry and temperature. These patterns demonstrate that glacial periods affected the entire Earth system, influencing atmosphere, land, and oceans simultaneously. The last glacial maximum offers a window into how Earth responds to extreme cold. It demonstrates the interplay of ice sheets, atmospheric gases, ocean currents, vegetation, and human adaptation. By studying this period, scientists gain insight into the sensitivity of the climate system, the timescales of change, and the capacity of life to adjust. It provides a baseline for comparison with current warming trends, showing the magnitude of natural climate shifts and how they shape the planet. Every layer of ice, every fossilized plant, and every ancient air bubble contributes to a detailed understanding of this frozen world. The lessons embedded in these records guide our comprehension of both past and potential future climate dynamics. The rhythm of Earth's climate is not random. Over tens of thousands of years, the planet experiences predictable variations in its orbit, tilt, and orientation relative to the Sun. These variations, known collectively as Milankovitch cycles, influence how much solar energy reaches different parts of the planet and, in turn, affect the growth and retreat of ice sheets. Named after the Serbian scientist Milutin Milankovic, who first described them in the early 20th century, these cycles offer a key to understanding the timing of ice ages. They operate on three main timescales, each with a measurable impact on climate. The first, eccentricity, refers to changes in the shape of Earth's orbit around the Sun. The orbit shifts from more circular to more elliptical, roughly every 100,000 years. When the orbit is more elliptical, the distance between Earth and the Sun varies more significantly over the year, creating subtle changes in seasonal energy distribution. These changes, though small in absolute terms, can initiate feedbacks in the climate system, gradually affecting ice sheet size and global temperature. The second cycle, axial tilt or obliquity, describes the angle of Earth's axis relative to its orbital plane. This tilt oscillates between approximately 22 and 24.5 degrees over roughly 41,000 years. Greater tilt amplifies the contrast between summer and winter, while smaller tilt reduces it. When summer is warmer in high latitudes, ice sheets are more likely to melt. Conversely, cooler summers allow ice to persist and grow, eventually spreading across large areas. Ice cores and sediment records show correlations between changes in tilt and ice volume, providing evidence for the role of axial variation in past glaciations. The isotopic composition of oxygen in deep-sea sediments often reflects these cycles, revealing a clear pattern of temperature and ice fluctuations over tens of thousands of years. The third component, precession, is the wobble of Earth's axis, completing a cycle roughly every 26,000 years. This wobble changes the timing of seasons relative to Earth's position in its orbit. For example, if the northern hemisphere summer occurs when Earth is closest to the Sun, summers will be warmer. If it occurs when Earth is farther from the Sun, summers will be cooler. These variations can trigger shifts in ice sheet growth and decay. Precession interacts with tilt and eccentricity, creating periods of constructive and destructive interference that influence the intensity of glacial and interglacial periods. Paleoclimate studies use mathematical models to show how combinations of these cycles match the timing of ice age cycles recorded in sediment cores, revealing the precision with which orbital mechanics can influence climate. Data from deep-sea sediment cores provide a continuous record of climate change over millions of years. Tiny shells of plankton preserved in layers of sediment contain isotopes of oxygen that vary with temperature and ice volume. By measuring the ratio of oxygen 18 to oxygen 16, scientists can reconstruct past ocean temperatures and estimate the size of continental ice sheets. These isotopic records often align with the timing predicted by Milankovitch cycles, confirming the connection between orbital variations and glacial events. Similarly, ice cores from Greenland and Antarctica preserve trapped air bubbles that record past carbon dioxide levels, offering a glimpse of how atmospheric composition changed in tandem with orbital-driven climate shifts. Each layer in these ice cores represents a snapshot of the climate, with the thickness and composition revealing the rhythm of snowfall, temperature, and greenhouse gas concentration over time. Milankovitch cycles explain why ice ages have a quasi-regular timing, but do not act alone. Their influence is amplified or dampened by feedbacks in the Earth system. For example, as ice sheets expand, they increase the reflectivity or albedo of the surface, causing more sunlight to be reflected and further cooling the planet. Conversely, when ice melts, darker land and ocean surfaces absorb more energy, reinforcing warming. Greenhouse gas concentrations respond to these changes, either reinforcing cooling or warming trends. The combination of orbital forcing and feedbacks explains the magnitude of glacial and interglacial periods recorded in paleoclimate data. It also accounts for variations between different ice ages, as not every cycle produces the same response due to interactions with volcanic activity, ocean circulation, and atmospheric composition. Seasonal patterns are affected as well. When Earth's orbit and tilt produce cooler summers in high latitudes, snow and ice persist year-round, leading to a gradual build-up of ice sheets. This process unfolds over thousands of years, with each season contributing to long-term accumulation or melting. Precipitation patterns also shift in response to temperature gradients and changes in atmospheric circulation. Sediment layers in lakes and oceans capture these variations, recording differences in rainfall, wind-blown dust, and vegetation cover. Fossil pollen from these sediments provides further detail, showing how plants responded to gradual shifts in climate. By integrating these records, scientists can reconstruct not only the presence of ice sheets, but also the broader environmental conditions surrounding them. The connection between orbital cycles and climate is evident in the timing of the last several ice ages. Glacial periods often began when eccentricity, tilt, and precession combined to produce cooler summers in the northern hemisphere. Interglacial periods, like the one we live in today, occurred when orbital conditions favored warmer summers, allowing ice sheets to retreat. These cycles help explain why ice ages are spaced tens of thousands to over 100,000 years apart. The timing is not exact, as the Earth system contains internal variability, but the broad pattern aligns closely with predictions based on orbital mechanics. This correspondence demonstrates the power of natural astronomical forces in shaping climate over long timescales. Understanding Milankovitch cycles also provides context for evaluating modern climate change. While orbital variations continue, their influence is currently small compared to the rapid warming caused by greenhouse gas emissions. However, these cycles remain a fundamental part of Earth's climate system. They illustrate how small changes in solar energy distribution, when combined with feedbacks in ice, ocean, and atmosphere, can trigger profound transformations over millennia. They remind us that Earth's climate is highly sensitive to shifts in energy balance, whether caused by orbital forcing or human activity. Paleoclimate records offer a detailed framework, showing that natural climate change can be gradual yet powerful, shaping ecosystems, landscapes, and life on Earth. By studying these cycles, scientists gain insight into both the timing and magnitude of Ice Age events. The patterns preserved in sediments, ice, and fossils reveal the interplay between astronomical factors and Earth's internal systems. They demonstrate that climate is the product of interconnected forces, responding over long periods to variations in sunlight, atmospheric composition, and surface conditions. This understanding lays the groundwork for predicting how current and future changes in greenhouse gas concentrations might interact with natural cycles, providing a deeper perspective on the potential for cooling or warming in the centuries to come. Each observation adds to a growing picture of the delicate balance that controls the rise and fall of ice sheets, the advance and retreat of glaciers, and the rhythm of climate across geological time. Today, Earth's climate is changing in ways that are both rapid and measurable. Unlike past ice ages, where shifts occurred over thousands of years, current changes are unfolding within decades. Scientists attribute much of this warming to human activity, primarily the release of greenhouse gases into the atmosphere. Carbon dioxide, methane, and nitrous oxide trap heat, preventing it from escaping into space. Measurements from atmospheric monitoring stations, such as the Mauna Loa Observatory in Hawaii, show a steady increase in carbon dioxide from around 280 parts per million before the Industrial Revolution to over 420 parts per million today. Methane levels have more than doubled, and nitrous oxide has risen steadily. These gases amplify the natural greenhouse effect, raising global temperatures in ways that are unprecedented in the recent geological record. Global temperature trends provide a clear picture of the warming Earth. Surface measurements from thousands of weather stations across the world indicate that the past century has seen a rise of approximately 1.2 degrees Celsius. This warming is not uniform. Some regions experience more rapid increases, particularly the Arctic, where temperatures are rising 2 to 3 times faster than the global average. Land areas heat faster than oceans, leading to changes in precipitation patterns, storm intensity, and seasonal cycles. Historical records, tree rings, and ice core data confirm that these rates of warming are faster than most natural fluctuations observed over the past tens of thousands of years, including the transitions between glacial and interglacial periods. Polar ice sheets are responding to this warming in significant ways. In Greenland, satellite observations show that ice mass is decreasing at a rate of roughly 280 billion tons per year. Meltwater flows into surrounding oceans, raising sea levels and contributing to changes in ocean circulation. In Antarctica, the pattern is more complex. While parts of the East Antarctic ice sheet remain relatively stable, the West Antarctic ice sheet and the Antarctic Peninsula are losing ice at an accelerating pace. Between 2002 and 2020, Antarctica lost an estimated 150 billion tons of ice per year on average, with some regions experiencing sudden, rapid collapse of ice shelves. These measurements come from satellite altimetry, radar, and gravity observations, which allows scientists to track changes in ice thickness, volume, and flow with high precision. Glacial retreat is also visible in mountain ranges worldwide, from the Alps to the Himalayas, further confirming the global reach of current warming. Sea ice in the Arctic is particularly sensitive to temperature increases. Observations show a marked decline in both the extent and thickness of summer sea ice over the past few decades. In the 1980s, the Arctic typically retained larger areas of multi-year ice that persisted through several summers. Today, most ice is seasonal, forming in winter and melting almost entirely in summer. This reduction alters the surface albedo, meaning less sunlight is reflected back into space, which in turn accelerates warming in the region. Satellite imagery and passive microwave measurements provide continuous monitoring, showing year-to-year variations alongside long-term decline. The Antarctic sea ice presents a more complex picture, with some areas showing slight increases in extent while others decrease. But the overall trend, particularly in the southern oceans surrounding West Antarctica, indicates thinning and seasonal instability. Atmospheric measurements complement these observations by tracking temperature, humidity, and circulation patterns. Radiosondes, balloons that ascend through the atmosphere, provide vertical profiles of temperature and moisture. Aircraft and satellites measure radiation and cloud cover, helping scientists understand how heat is distributed across the globe. Data show shifts in jet streams, changes in monsoon patterns, and increased frequency of extreme heat events. These changes interact with ocean currents and ice sheets, creating feedback loops that amplify warming. Unlike the gradual cooling that led to past ice ages, these rapid changes demonstrate the capacity of human influence to override some natural climate rhythms, at least temporarily. Comparing current warming trends to historical cooling periods highlights the uniqueness of today's climate. Ice Age onset required tens of thousands of years of gradual change in temperature, often triggered by orbital variations, volcanic activity, or shifts in ocean circulation. The rate of temperature change during these periods rarely exceeded a few tenths of a degree per century. In contrast, the modern increase of more than 1 degree Celsius within a single century is extraordinary in the context of the last 20,000 years. Paleoclimate records, including ice cores and ocean sediments, show that the planet has not experienced warming of this speed since the end of the last glacial period. This rapidity increases the stress on ecosystems, ice sheets, and human societies, as adaptation is required on timescales far shorter than those allowed by natural climate cycles. The distribution of warming across the planet affects both weather and longer-term climate patterns. Higher temperatures lead to increased evaporation from oceans, contributing to heavier rainfall and more intense storms in some regions, while others experience drought due to shifting pressure systems. Ocean heat content has risen significantly, with the top 2,000 meters of the ocean absorbing more than 90% of excess heat. This warming affects currents, including the Atlantic meridional overturning circulation, which plays a critical role in regulating climate across the northern hemisphere. Melting ice and thermal expansion of seawater are primary contributors to rising sea levels, threatening coastal ecosystems and human settlements. Observing changes over time, scientists note that the Arctic and Antarctic provide early warning of broader climate impacts. Glacial retreat, permafrost thaw, and sea ice loss release greenhouse gases such as carbon dioxide and methane, reinforcing warming trends. Seasonal patterns shift, affecting the timing of plant growth, animal migrations, and ice formation. Phenological studies, tracking the timing of biological events, reveal changes in breeding, flowering, and migration, demonstrating the biological consequences of warming. These observations, combined with precise measurements from satellites, sensors, and long-term monitoring stations, create a detailed record of current climate dynamics. The current warming trend illustrates the interconnectedness of Earth's systems. Ice sheets, ocean currents, atmospheric composition, and solar energy all interact. But human influence now dominates the pace of change. Unlike natural cooling events that slowly shaped landscapes and ecosystems, modern warming unfolds with unprecedented speed. While the magnitude of temperature change might eventually match some historical fluctuations, the rate is far faster, leaving less time for ecosystems and human societies to adjust. Understanding these trends requires integrating data from multiple sources: ice cores, satellite observations, ocean measurements, and atmospheric sampling. Each dataset contributes to a comprehensive view of Earth's current climate trajectory. By comparing modern warming to historical glacial periods, scientists gain perspective on the uniqueness of today's situation. Ice ages, including the last glacial maximum, were shaped by slow natural cycles, allowing time for ecosystems and humans to migrate and adapt. Current warming, in contrast, is forcing rapid adjustments in glaciers, sea ice, ocean circulation, and biological systems. Monitoring these trends informs predictions for the future, helping to assess potential impacts on global sea levels, weather patterns, and climate-sensitive regions. The evidence is clear. Earth's climate is warming at a pace unmatched by natural processes over the last several tens of thousands of years, highlighting both the influence of humans and the sensitivity of the planet to shifts in greenhouse gas concentrations. The oceans are a vast and moving system, carrying heat and energy across the planet. One of the most important components of this system is the Atlantic Meridional Overturning Circulation, often called the AMOC. This circulation acts like a giant conveyor belt, transporting warm surface water from the tropics toward the North Atlantic and sending cold, dense water back toward the deep ocean. In doing so, it redistributes heat, moderates climate, and affects weather patterns across the globe. The strength and stability of the AMOC play a critical role in maintaining the climate balance that supports life in many regions. Its influence stretches from tropical seas to polar ice, shaping temperature and rainfall patterns in a way that is both continuous and subtle, yet profoundly important. Warm waters from the equator move northward along the surface. As the water reaches higher latitudes, it cools, becomes denser, and sinks into the deep ocean. This process drives the circulation of water across the Atlantic, linking surface and deep layers. Heat transported by the AMOC keeps parts of Europe and North America warmer than they would be otherwise. Without this heat, Northern Europe would experience much colder winters, and parts of the eastern United States would also be affected. The circulation influences not only temperature, but also precipitation, storm intensity, and seasonal weather patterns. Changes in the flow of the AMOC can have cascading effects on the global climate system, including shifts in monsoon patterns in Africa, droughts in South America, and changes in ocean productivity. Recent observations suggest that the AMOC has weakened compared to historical measurements. Scientists monitor the circulation using a combination of satellites, ocean floats, and ship-based instruments. These tools measure surface temperature, salinity, and currents at various depths. Data collected over the past decades indicate a slowdown in the northward flow of warm water and in the sinking of dense water in the North Atlantic. The causes are complex, including the addition of fresh water from melting Greenland ice, increased rainfall, and changes in salinity patterns. Fresh water makes the surface water less dense, slowing the sinking process that drives the circulation. This weakening is a concern because it can disrupt the distribution of heat, potentially altering climate patterns across the Northern Hemisphere. Slowing of the AMOC can influence regional climates in noticeable ways. In Europe, reduced northward heat transport could lead to cooler winters despite global warming. This counterintuitive effect occurs because heat that would normally warm the region remains farther south or is mixed differently within the ocean. In North America, the eastern seaboard and parts of the Midwest may experience shifts in storm tracks and precipitation. Changes in the AMOC also affect the tropics. The West African monsoon, which brings essential rainfall to large parts of the Sahel, is sensitive to the heat distribution across the Atlantic. A slowdown in circulation can weaken the monsoon, causing drought and impacting agriculture and ecosystems. Similarly, rainfall patterns in the Amazon and South America are linked to oceanic heat transport, showing that even distant regions feel the effects of changes in the Atlantic. Ice melt in Greenland is a significant factor influencing the AMOC. As the ice sheet loses mass, large volumes of fresh water enter the surrounding ocean, reducing salinity and density in surface waters. Observations show that ice loss in Greenland has accelerated in recent decades, adding to the freshwater input. This freshening of the ocean surface can interfere with the sinking of cold, dense water that drives the AMOC. Models predict that continued melting could weaken the circulation further, leading to larger shifts in climate patterns. The combination of ice loss, warming waters, and altered salinity creates feedbacks that are complex but increasingly measurable. Scientists use computer simulations alongside direct measurements to understand the current trajectory and potential future scenarios of the AMOC. Satellite data provide detailed views of ocean surface temperature and height, indicating changes in circulation patterns. The Argo program, which deploys thousands of autonomous floats across the oceans, measures temperature, salinity, and currents at different depths. These floats reveal patterns of slow-moving warm water, changes in density, and shifts in deep water formation. Observations indicate that the strength of the AMOC has decreased by roughly 10 to 15% over the past century. While natural variability plays a role, the trend is concerning because it suggests that human influence and ongoing ice melt are altering the behavior of this critical system. Continuous monitoring is essential to track changes, understand potential impacts, and refine predictions about the future climate. The influence of ocean currents extends to extreme weather events. Hurricanes and cyclones are fueled by ocean heat, and shifts in circulation can alter their formation and intensity. A weaker AMOC affects sea surface temperatures in the Atlantic, which may change the number, strength, and path of storms. In addition, the transport of nutrients in the ocean, vital for marine ecosystems, is linked to circulation patterns. Slower currents can reduce the mixing of deep and surface waters, affecting phytoplankton growth and the food web that depends on it. Fisheries, carbon absorption, and ocean productivity are all linked to the strength and stability of the AMOC, highlighting the wide-reaching implications of changes in ocean currents. Long-term climate patterns are tightly connected to ocean circulation. Past abrupt cooling events, such as the Younger Dryas approximately 12,000 years ago, are thought to have involved sudden disruptions of the AMOC. During this event, temperatures in the North Atlantic region dropped rapidly, demonstrating the sensitivity of regional climates to changes in ocean heat transport. Ice cores, sediment layers, and isotopic analysis provide evidence of these shifts. Studying such past events helps scientists understand the potential consequences if the AMOC continues to weaken under current warming and ice melt. The comparison shows that even subtle changes in the flow of heat through the ocean can produce significant regional climate effects. The AMOC does not act in isolation. It interacts with the atmosphere, sea ice, and other ocean currents. For instance, warmer waters in the tropics drive evaporation, influencing humidity, rainfall, and wind patterns. These atmospheric changes feed back into the ocean, affecting currents and temperature distribution. The polar regions are particularly important because the formation of dense water relies on cold temperatures and high salinity. As polar ice melts and freshwater input increases, this mechanism weakens, demonstrating the interconnectedness of climate systems. Each element, the atmosphere, ocean, ice, and land, affects the others, creating a dynamic equilibrium that determines the distribution of heat and the behavior of weather patterns across the globe. Understanding the role of the AMOC is crucial for predicting future climate. Models show that continued greenhouse gas emissions and ice sheet melt could further weaken the circulation over the next century. Such a slowdown could influence temperature and precipitation in Europe, North America, and the tropics, with potential effects on agriculture, ecosystems, and human societies. By observing current trends, measuring ocean properties, and comparing them with historical events, scientists can anticipate potential disruptions. The study of ocean currents demonstrates that climate is a global system, in which changes in one region can ripple across continents and oceans, influencing the environment in ways that are slow, observable, and deeply interconnected. Earth's climate system contains feedbacks that can either strengthen or weaken changes in temperature. These feedbacks act like amplifiers or dampeners, influencing how warming or cooling spreads across the planet. One of the most important positive feedbacks is the albedo effect. Ice and snow reflect sunlight, keeping the surface cool. When ice melts, darker surfaces such as ocean water or land are exposed. These surfaces absorb more sunlight, raising local temperatures and accelerating ice loss. In the Arctic, this process is particularly noticeable. Satellite images show that the area covered by sea ice has decreased sharply in recent decades, revealing darker ocean surfaces that warm more rapidly. Each summer, the loss of reflective ice contributes to further melting in the following years, creating a self-reinforcing cycle. Another critical positive feedback involves permafrost. Vast regions in the Arctic and subarctic contain frozen soils rich in organic matter. When permafrost thaws, microbes decompose this material, releasing greenhouse gases, mainly carbon dioxide and methane, into the atmosphere. Methane is especially potent, trapping heat much more efficiently than carbon dioxide over short timescales. Observations using ground measurements, satellites, and atmospheric sampling indicate that permafrost regions are warming faster than the global average. This thawing releases greenhouse gases that amplify warming, which in turn promotes more permafrost melt. The feedback is gradual but persistent, with the potential to release hundreds of billions of tons of carbon over the next century if current trends continue. Models estimate that permafrost emissions could contribute significantly to global warming, particularly in the high northern latitudes. Cloud cover provides both positive and negative feedbacks. Clouds can reflect incoming sunlight, cooling the surface, or trap infrared radiation, warming the atmosphere. The balance between these effects depends on cloud type, altitude, thickness, and location. Low, thick clouds tend to cool by reflecting sunlight, while high, thin clouds contribute to warming by trapping heat. Changes in temperature, humidity, and circulation patterns influence cloud formation, which in turn modifies temperature. Observations from satellites and weather stations reveal that cloud cover is changing in response to warming, though the patterns are complex. Clouds over the tropics have shifted in some regions, altering rainfall distribution, while polar clouds influence ice melt by modifying the amount of sunlight reaching the surface. This feedback system is dynamic, responding to both natural variability and human-induced changes in greenhouse gases. Vegetation also participates in climate feedbacks. Forests and grasslands influence the amount of sunlight absorbed or reflected, the release of carbon dioxide, and local moisture patterns. As temperatures rise, some regions see increased plant growth, absorbing carbon from the atmosphere, which can partially counteract warming. In other regions, drought, heat stress, and wildfire reduce vegetation, releasing stored carbon and reinforcing warming. Satellite data and ground observations show that the balance of vegetation feedbacks is shifting as the planet warms, with positive feedbacks currently outweighing negative ones in many areas. The expansion of forests into higher latitudes can offset some warming, but this effect is limited by soil quality, temperature, and seasonal light availability. Ocean feedbacks are equally important. Warmer surface waters reduce the ocean's ability to absorb carbon dioxide, leaving more greenhouse gas in the atmosphere. This decreases the natural cooling effect of the ocean and accelerates warming. At the same time, melting ice sheets contribute fresh water that alters circulation patterns, affecting heat transport. Ocean models indicate that the combination of warming, ice melt, and changes in salinity could weaken large currents like the AMOC, further amplifying regional temperature changes. Satellite measurements of sea surface temperature, salinity, and currents provide a detailed picture of these interactions, revealing both short-term variability and long-term trends. Snow cover beyond large ice sheets also contributes to feedback loops. Mountain snow reflects sunlight, maintaining cooler local temperatures. Early snowmelt exposes darker ground, which absorbs heat and reinforces warming. Observations in the Himalayas, Rockies, and Andes show that snow is melting earlier in spring, contributing to increased runoff and local warming. This change affects not only temperature, but also water availability for ecosystems and human communities. The combination of snow and ice feedbacks forms a network that links polar and mountainous regions to global climate, illustrating how local changes can propagate across the planet. Volcanic and aerosol interactions provide additional feedbacks, sometimes cooling the planet temporarily. Volcanic eruptions release particles and gases that reflect sunlight. In the short term, large eruptions can offset some warming, producing temporary cooling. However, these effects last only a few years and are generally small compared to long-term greenhouse gas-driven warming. Human-produced aerosols also influence temperature and precipitation patterns. Industrial emissions and air pollution can cool the surface by reflecting sunlight, but they may also alter cloud formation and regional rainfall. The feedbacks associated with aerosols are complex, often varying by location and season, but they highlight the intricate balance between natural and human-induced forces in the climate system. Sea ice, beyond reflecting sunlight, interacts with ocean and atmospheric circulation. Reduced sea ice affects wind patterns, storm tracks, and heat transport from the ocean to the atmosphere. Satellite observations show that changes in Arctic sea ice are already modifying weather patterns in the Northern Hemisphere. Winters in parts of North America and Eurasia can experience unusual cold spells due to shifts in the jet stream influenced by the loss of ice. At the same time, warmer Arctic temperatures influence permafrost, vegetation, and cloud formation, creating interconnected feedbacks that combine to reinforce warming or modify seasonal patterns. Feedback mechanisms are not only present today, but also operated in the past during ice age cycles. During the last glacial period, Expanding ice sheets increased albedo, promoting further cooling. As ice melted, lower albedo surfaces absorbed heat, accelerating warming. Methane released from thawing permafrost or wetlands amplified temperature changes. Clouds and vegetation also influence the pace of ice sheet growth and decay. These historical feedbacks can be observed in ice cores, sediment records, and isotopic analysis, showing that the climate system has long been sensitive to small changes in temperature, greenhouse gas concentrations, and surface properties. Current data provide measurable evidence of these feedbacks at work. Arctic amplification, where temperatures rise faster than the global average, illustrates the combined effects of albedo loss, permafrost thaw, and cloud changes. Measurements of methane concentrations above thawing tundra reveal ongoing emissions, while satellite imaging confirms ice and snow loss. Ocean heat content and carbon absorption trends indicate the reinforcement of warming through feedback loops. Climate models integrate these observations to predict future scenarios. They show that if greenhouse gas emissions continue at current rates, positive feedbacks will likely accelerate warming, while negative feedbacks, such as increased plant growth in some regions, may provide only partial mitigation. These mechanisms highlight the sensitivity and interconnectedness of the Earth system, demonstrating that small changes in one part of the system can influence the climate globally. By understanding feedback mechanisms, scientists gain insight into the pace and magnitude of climate change. The combined effects of albedo, permafrost, clouds, vegetation, oceans, and aerosols form a network that amplifies or moderates temperature shifts. Observing these processes in real time, using satellites, field measurements, and atmospheric data, allows researchers to anticipate future changes with greater precision. Feedbacks illustrate that Earth's climate is not static. It responds dynamically to both natural and human influences. This understanding provides context for interpreting current warming trends and assessing the potential for abrupt or gradual shifts in climate, including how natural cooling, such as a future ice age, might interact with ongoing human-induced warming. Earth's climate is shaped not only by internal systems, but also by forces from outside and occasional extreme events. Volcanic eruptions are one of the most visible external influences. Large eruptions release ash, dust, and gases, including sulfur dioxide, into the atmosphere. When sulfur dioxide reaches the stratosphere, it forms tiny droplets that reflect sunlight back into space, temporarily cooling the surface. Historical records and ice cores provide evidence of these short-term effects. For example, the eruption of Mount Tambora in 1815 caused the year without a summer in 1816, leading to crop failures, cooler temperatures, and widespread disruptions across Europe and North America. While volcanic cooling is usually temporary, lasting from months to a few years, repeated eruptions or very large events can produce longer-lasting effects on regional climate. The influence of volcanism is well documented, and scientists use both historical data and climate models to quantify its effects on temperature and precipitation. Solar activity also plays a role in climate variability. The Sun goes through cycles of roughly 11 years, characterized by fluctuations in sunspots, solar flares, and total solar radiation. Periods of low solar activity, such as the Maunder minimum in the 17th century, have been associated with slightly cooler temperatures in parts of the Northern Hemisphere. Proxy data, including tree rings and ice cores, show correlations between prolonged solar minima and regional cooling events. While variations in solar output contribute to natural climate variability, the magnitude of solar forcing is small compared to the warming caused by modern greenhouse gas emissions. Scientists measure solar irradiance using satellites, comparing current output with historical proxies to understand its influence on both short-term weather patterns and longer-term climate trends. Meteorite impacts, though rare, are another external factor that can influence climate. Large impacts release enormous amounts of energy, dust, and aerosols into the atmosphere, blocking sunlight and causing abrupt cooling. Geological evidence, such as impact craters and layers of iridium-rich sediment, indicates that past meteorite events have had measurable effects on global climate and ecosystems. The most famous example is the Chicxulub impact around 66 million years ago, which contributed to mass extinctions and a period of severe cooling. While such impacts are extremely uncommon, their potential influence demonstrates that external shocks can alter climate quickly and dramatically, even if they do not dictate long-term patterns like ice ages. Orbital forcing, already discussed in detail in relation to Milankovitch cycles, remains a key external influence on glacial cycles. Variations in Earth's orbit, axial tilt, and precession change the distribution of sunlight across the planet. These changes trigger slow, predictable climate shifts that can promote glacial advance or retreat over tens of thousands of years. External events like volcanism or meteorite impacts may superimpose short-term variations on these longer-term cycles, creating complex interactions in the climate system. By combining orbital forcing with paleoclimate data, scientists can reconstruct periods of glacial expansion and retreat, revealing how sensitive the planet is to changes in solar energy distribution. The magnitude and duration of these external factors vary widely. Volcanic eruptions can produce cooling of up to 1 degree Celsius over a year or two, but their effects diminish as aerosols settle. Solar variations contribute fluctuations of less than 1/10 of a degree per decade, influencing regional temperatures more than global averages. Meteorite impacts can cause abrupt temperature drops of several degrees, lasting months or years depending on the scale of the event. Compared to these influences, orbital forcing shapes climate over thousands to hundreds of thousands of years, producing ice age cycles that dominate the geological record. Scientific consensus indicates that while short-term events affect climate temporarily, the long-term rhythm of glacial and interglacial periods is primarily governed by orbital mechanics and internal feedbacks. Ice core records provide evidence of volcanic and solar influences. Layers containing volcanic ash or sulfate correspond to known eruptions, allowing scientists to date events and measure their cooling effects. Tree rings reveal periods of reduced growth, linked to cooler temperatures following large eruptions or low solar activity. These proxies, combined with instrumental records and satellite observations, offer a detailed picture of how external factors interact with internal climate systems. By comparing multiple sources of evidence, researchers can distinguish between short-term perturbations and long-term trends, showing that volcanism and solar variability, while important, cannot by themselves trigger major ice ages. Interactions between volcanic eruptions and solar activity can produce amplified effects. For instance, if a major eruption occurs during a solar minimum, the combined reduction in incoming energy and increased reflection from aerosols can result in more pronounced cooling than either factor alone. Historical examples, including the Little Ice Age from the 14th to the 19th century, suggest that clusters of low solar activity and frequent eruptions may have contributed to cooler conditions in parts of Europe and North America. These interactions illustrate that climate is influenced by multiple external and internal factors, each adding to the complexity of observed temperature changes. External factors also interact with feedback mechanisms. A volcanic eruption that reduces sunlight can increase snow and ice accumulation temporarily, enhancing albedo and further cooling the surface. Conversely, solar maxima may slightly accelerate melting in polar regions, affecting permafrost and sea ice. These combined effects are measurable but small compared with the rapid warming caused by human greenhouse gas emissions today. By studying these interactions, scientists gain insight into the sensitivity of the climate system, its ability to respond to perturbations, and the limits of natural forcing in producing large, long-term climate shifts such as ice ages. While volcanic eruptions, solar cycles, and meteorite impacts are measurable and important for understanding short-term climate variability, their role in initiating or ending ice ages is limited compared with orbital forcing and internal feedbacks. The paleoclimate record shows that ice ages develop over tens of thousands of years in response to small changes in solar distribution, amplified by feedback such as ice albedo effects, greenhouse gases, and ocean circulation. External events may accelerate or delay certain processes, but do not dictate the overall timing or magnitude of glacial periods. This understanding comes from integrating geological evidence, ice cores, sediment studies, and climate modeling, creating a robust scientific framework for interpreting both past and present climate change. By combining observations of external factors with paleoclimate data, scientists can place current changes in perspective. Volcanic cooling is temporary, solar cycles are moderate, and meteorite impacts are rare. In contrast, the current rate of warming caused by human activity far exceeds natural external influences. Understanding these distinctions helps clarify why ice ages occur slowly, while contemporary warming is rapid. Studying external factors alongside internal mechanisms reinforces the understanding that the climate system is sensitive, interconnected, and influenced by multiple scales of forcing. This insight provides context for predicting the potential onset of future ice age conditions and the interplay between natural variability and human impact. Scientists use climate models to understand how the Earth might behave in the future. These models simulate the interactions between the atmosphere, oceans, ice, and land. By inputting physical laws and observed data, researchers can project how temperature, precipitation, and ice coverage may change over decades or centuries. For predicting potential cooling events, including future ice ages, models take into account orbital variations, greenhouse gas concentrations, volcanic activity, solar cycles, and feedback mechanisms like albedo and permafrost thaw. Running these models helps determine whether natural cooling trends could override modern warming or if human influence dominates the climate system. Model simulations show that ice ages develop slowly, typically over tens of thousands of years. The combination of orbital forcing and feedback loops sets the stage for glacial expansion. Cooler summers in high northern latitudes allow snow and ice to accumulate year after year, gradually building massive ice sheets. Sea levels drop as water becomes locked in ice, and ocean currents respond to changes in salinity and temperature. These processes take millennia to unfold. Even the strongest positive feedbacks, such as increased ice albedo or permafrost carbon release, work on similar timescales. Abrupt cooling events like the Younger Dryas demonstrate that rapid shifts are possible, but they are usually triggered by rare disruptions, such as large freshwater influxes into the North Atlantic, and are superimposed on longer-term trends. Recent models have explored scenarios in which parts of the AMOC weaken or collapse, potentially producing short-term regional cooling. Simulations show that a significant slowdown could cool parts of northern Europe by several degrees Celsius, despite ongoing global warming. This effect occurs because heat transport from the tropics diminishes, while the tropics and southern hemisphere continue to warm. Sea ice models indicate that if temperatures were to decline in this way, Arctic ice would expand, reflecting more sunlight and reinforcing local cooling. However, global temperature remains elevated in these scenarios because the underlying forcing from greenhouse gases dominates. These model results highlight the difference between regional cooling effects and true ice age conditions, which require long-term reductions in global temperatures. Some models consider the possibility of extreme volcanic eruptions or persistent low solar output contributing to abrupt cooling. In simulations, a cluster of very large eruptions can reduce global average temperature by 1 degree Celsius or more for several years. If these events coincided with orbital conditions favoring cooler summers in the northern hemisphere, they might slightly accelerate glacial growth. However, the probability of this combination occurring in the mid-21st century is extremely low. Solar minima have limited impact on global temperatures compared to the effect of rising greenhouse gases and volcanic eruptions, while influential for a few years, do not produce sustained cooling capable of initiating an ice age under current conditions. Temperature projections from climate models indicate that by 2050, the planet is expected to be warmer than pre-industrial times, by approximately 1.5 to 2 degrees Celsius, depending on emissions scenarios. Warming is projected to be stronger over land and at high latitudes. In these scenarios, sea ice continues to decline, glaciers shrink, and ice sheets lose mass, especially in Greenland and West Antarctica. Even if orbital conditions favored cooling, the human-driven greenhouse effect is too strong for a mid-century ice age to occur. Models consistently show that modern warming overwhelms natural cooling factors on timescales of decades to a few centuries. Sea ice simulations reinforce these conclusions. Arctic summer ice extent continues to shrink in all scenarios, and thickness diminishes as well. Seasonal variability still occurs, but the long-term trend is clear. Ice is losing ground. Antarctic sea ice remains more stable, but coastal ice shelves are thinning and retreating. Ocean heat content rises, and deep water formation is affected, altering the AMOC. Model experiments confirm that while partial regional cooling can occur, especially if currents slow, the expansion of ice sheets large enough to define an ice age is not projected for the mid-21st century. Ice age initiation requires sustained cooling over millennia, which is not present in these projections. AMOC modeling provides further insight. Simulations of weakening circulation show regional temperature changes, shifts in precipitation, and impacts on storm patterns, but global cooling is modest. Even a near collapse of the AMOC does not counteract the overall warming from greenhouse gases. Models reveal that changes in heat distribution can produce local or temporary cooling, but they cannot trigger the planetary-scale glaciation associated with ice ages under current atmospheric conditions. These findings emphasize the resilience of human-driven warming relative to natural variations in ocean circulation. Feedback mechanisms are incorporated into these models to test their influence. Ice albedo effects, permafrost carbon release, and cloud changes are included to understand potential amplifications or mitigations. Results suggest that positive feedbacks enhance warming rather than promoting cooling given current conditions. While models indicate that ice growth could be modestly accelerated under ideal orbital scenarios, the magnitude is insufficient to produce a new ice age by 2050. Predictions are robust across multiple independent climate models, satellite observations, and paleoclimate reconstructions. The consensus is that near-term natural cooling is extremely unlikely, and warming will continue to dominate the climate system. In addition to physical models, probabilistic assessments are used to evaluate the likelihood of abrupt cooling. Studies combining orbital mechanics, greenhouse gas trajectories, and ocean circulation suggest that the probability of a significant ice age event occurring in the mid-21st century is close to zero. Scenarios showing partial regional cooling, such as in Europe due to AMOC slowdown, are plausible. But global ice sheet growth on the scale of the last glacial maximum is not supported by any credible simulation. The models emphasize that while natural variability continues, it is now dwarfed by anthropogenic influence, making ice age onset in the near future practically impossible. Overall, predictive modeling provides a clear view of the climate trajectory. Ice age conditions require a long-term, gradual reduction in global temperatures, supported by orbital forcing and amplified by feedbacks. Current greenhouse gas concentrations, ongoing ice melt, and ocean heat content oppose these conditions, creating a climate environment strongly biased toward warming. Models show that while local cooling may occur in specific regions or during short-term events, the overall trend is toward higher temperatures, reduced ice cover, and altered circulation patterns. This understanding reinforces the conclusion that a new ice age in 2050 is not supported by scientific evidence. These simulations integrate data from multiple sources, satellite observations of temperature, ice, and ocean currents, ground-based climate measurements, paleoclimate reconstructions, and physics-based models of energy balance. The results consistently show that the rate of modern warming outpaces natural cooling mechanisms. Ice sheet growth, sea ice expansion, and ocean circulation changes cannot occur rapidly enough to produce a mid-century ice age. Even under extreme hypothetical scenarios, cooling is modest and temporary. Climate models provide not only projections, but also context, showing that while the Earth system is sensitive to natural and external factors, current conditions are dominated by human influence, preventing the onset of a new glacial period in the near future. Human activity has become the dominant force in shaping the climate, affecting the natural rhythms that would otherwise govern cooling and glacial cycles. The release of greenhouse gases, primarily carbon dioxide, methane, and nitrous oxide, has steadily increased since the Industrial Revolution. Fossil fuel combustion, deforestation, and industrial processes contribute to the accumulation of these gases in the atmosphere. Observations from air monitoring stations show that carbon dioxide concentrations have risen from roughly 280 parts per million before industrialization to over 420 parts per million today. This increase strengthens the greenhouse effect, trapping more heat and raising global temperatures. The magnitude of this human influence is so large that it overwhelms the slow, gradual cooling expected from natural orbital variations and feedbacks that might otherwise lead toward a new ice age. Greenhouse gas emissions affect every component of the climate system. Ice sheets respond slowly to warming, but the persistent rise in temperature contributes to melting in Greenland and Antarctica. Sea ice diminishes, reducing the reflective surface and further amplifying warming. Oceans absorb heat and carbon dioxide, altering currents and impacting global climate regulation. Forests and soils, which normally store carbon, are affected by changes in temperature, precipitation, and human land use, sometimes releasing stored carbon into the atmosphere. These processes demonstrate that human influence interacts with natural feedbacks in ways that suppress the potential for long-term cooling. Without human emissions, orbital cycles would likely produce gradual temperature reductions over millennia. But current emissions counteract this process, delaying or preventing ice sheet growth. Climate models incorporating human emissions show that continued greenhouse gas release strongly inhibits glacial initiation. Simulations using realistic CO2 trajectories indicate that even under orbital conditions favoring cooler summers in the Northern Hemisphere, the warming effect of anthropogenic gases prevents the accumulation of snow and ice necessary to trigger glacial expansion. Ice cores, historical temperature reconstructions, and paleoclimate data provide context for these projections, showing that natural cycles alone produce much slower temperature changes than those driven by modern emissions. The comparison makes it clear that human influence has altered the natural balance, suppressing the cooling signals that might otherwise set the stage for a future ice age. Some proposals have suggested geoengineering as a way to counteract warming or even induce cooling. These include techniques such as injecting aerosols into the stratosphere to reflect sunlight, enhancing ocean albedo, or artificially removing carbon dioxide from the atmosphere. While these approaches could, in theory, lower global temperatures temporarily, they carry significant uncertainties and potential risks. Models indicate that the effects would be uneven, with some regions cooling, while others experience changes in precipitation, storm patterns, or ocean circulation. Moreover, geoengineering does not restore natural climate cycles. It may temporarily mask warming, but cannot replicate the long-term glacial and interglacial processes driven by orbital forcing and feedbacks. The scientific consensus emphasizes that reducing greenhouse gas emissions remains the most reliable method for influencing long-term climate in a controlled and predictable manner. Evidence from current emissions and climate policy illustrates the ongoing influence of humans on natural cooling. National and global monitoring programs track fossil fuel use, land use changes, and atmospheric concentrations of greenhouse gases. Trends indicate continued growth in emissions despite efforts to transition to renewable energy, improve efficiency, and protect forests. Data show that carbon dioxide levels continue to rise, and methane emissions from agriculture, landfills, and energy production are increasing. These trends highlight the difficulty of offsetting human influence on climate and underscore the improbability that natural cooling could proceed as it would without human activity. The absorption of carbon dioxide by natural systems is another factor affecting the potential for future ice ages. Oceans take up roughly a quarter of anthropogenic CO2 emissions, but warming reduces their ability to absorb more carbon. Similarly, forests act as carbon sinks, but deforestation, fires, and drought diminish their effectiveness. These limitations mean that much of the CO2 released by human activity remains in the atmosphere for decades to centuries, continuously contributing to warming. Paleoclimate records show that CO2 has played a key role in past glacial cycles, with lower concentrations supporting ice sheet growth. Today's elevated levels effectively prevent similar cooling processes from taking hold on any meaningful timescale. Human land use also interacts with climate feedbacks. Agricultural expansion, urban development, and deforestation change surface albedo, moisture patterns, and local climate. While some modifications could theoretically enhance reflectivity, the net effect of modern land use is generally to increase warming. Changes in vegetation cover affect carbon storage and local temperatures, influencing atmospheric circulation and precipitation patterns. Satellite data and field measurements confirm that human land use modifies the surface energy balance, further suppressing natural cooling signals and reinforcing the greenhouse-driven warming trend. Urbanization contributes additional warming through the heat island effect, where built environments absorb and radiate heat more efficiently than natural landscapes. This effect is strongest in densely populated areas, but contributes to regional temperature trends that reinforce global warming. When combined with greenhouse gases and other human influences, these factors demonstrate the comprehensive nature of human impact on the climate. Local interventions, such as urban planning or forest restoration, can modify these effects somewhat, but they cannot overcome the dominant global warming signal driven by emissions. Policy responses to climate change are designed to mitigate warming, but also influence the potential for natural cooling. International agreements, renewable energy deployment, and emission reduction targets aim to limit greenhouse gas accumulation. If successful, these measures could slow the rate of warming and allow climate systems to stabilize over time. However, they do not directly restore the natural cooling mechanisms of glacial cycles, which require long-term decreases in global temperatures and the gradual buildup of ice. Observations from carbon monitoring networks show that progress in reducing emissions is uneven and slower than required to halt warming trends, reinforcing the conclusion that ice age initiation is suppressed by ongoing human activity. Scientific studies consistently show that even under optimistic emission reduction scenarios, the influence of humans continues to dominate natural cooling signals for at least the next several centuries. Climate projections indicate that CO2 concentrations will remain elevated, oceans will continue to absorb heat, and ice sheets will gradually lose mass. These conditions counteract orbital and feedback mechanisms that might otherwise encourage glacial growth. Evidence from modeling, emissions data, and observations demonstrates that humans have effectively shifted the climate trajectory away from a potential ice age and towards sustained warming, at least over the near and mid-term future. Human influence suppresses natural cooling through multiple pathways. Greenhouse gas emissions trap heat and delay ice sheet growth. Land use changes, deforestation, and urbanization modify surface energy balances. Permafrost, vegetation, and ocean systems respond in ways that reinforce warming. Geoengineering proposals may temporarily alter temperatures, but they do not recreate natural glacial cycles. Observational data, satellite measurements, and climate models collectively show that human activity dominates the climate system, preventing the initiation of a new ice age within the next decades. Without significant reductions in emissions and strategic management of carbon sinks, the natural processes that could trigger glaciation remain largely overridden by anthropogenic warming. As we look at the vast and ever-changing Earth, we can see how its climate has shifted over thousands and millions of years. Ice ages have come and gone, leaving behind glaciers, valleys, and layers of rock and sediment that tell a quiet story of cooling and warming. Each glacial period has been shaped by the careful balance of sunlight, greenhouse gases, ice, oceans, and wind. The planet has a remarkable ability to respond to small changes, amplifying them through feedbacks or balancing them through natural processes. These cycles remind us that Earth's climate is never fixed. It flows, shifts, and adjusts over time in a continuous and interconnected dance. Looking back at the last glacial maximum, we can imagine a world covered in ice sheets, with seas much lower and landscapes stark and open. Life adapted, humans migrated, and the planet slowly prepared for warmer times. Then, as the climate shifted, ice retreated, oceans rose, and ecosystems adjusted. Trees returned to tundra, animals moved, and humanity spread across lands now free of ice. These slow, deliberate changes reveal a pattern of balance and resilience, where small forces accumulate over long periods to create significant transformations. Observing these past changes helps us understand how sensitive the climate is, how it responds to both gradual and abrupt forces, and how even the smallest shifts can be magnified through natural feedbacks. Today, the planet is warmer than it has been for thousands of years. Greenhouse gas levels are high, ice sheets are retreating, and oceans hold more heat than before. While natural cycles continue in the background, they are now influenced and overshadowed by human activity. Climate models, measurements, and observations all show that the warming signal is dominant, and that the processes that might have started a new ice age are suppressed. Even the great forces of the Atlantic currents, feedback loops, and orbital cycles now interact with a system altered by human influence. It is a reminder of how one species can affect a planetary system in ways both profound and measurable. Understanding the complexity of these systems can be comforting. Even as temperatures change, ice melts and currents shift, the processes are slow on a human timescale. The Earth continues to function, distributing heat, forming clouds, growing plants, and supporting life. Feedbacks may amplify changes, but they also maintain balance over long periods. The oceans rise and fall, the seasons cycle, and the sun continues its steady path across the sky. Ice ages may not come for many thousands of years, but the continuity of natural processes assures us that the planet persists, responding in predictable ways to both natural and human influences. Observing the patterns of past ice ages, current warming, and potential future changes, we see that Earth's climate is resilient and dynamic. It can absorb shocks, redistribute energy, and adapt over long timescales. Mountains erode, glaciers form and retreat, forests grow and shrink, and oceans carry heat from one place to another. Even in periods of extreme change, life adapts and persists. Understanding these rhythms provides perspective, showing that while humans influence the climate today, The larger system continues to function in ways that are measurable, understandable, and ongoing. Even small details carry meaning. Snowflakes form and melt, sea ice drifts and fractures, clouds gather and dissipate. Each process is part of the larger system, linked and interdependent. Atmospheric circulation moves heat across continents, ocean currents carry energy to distant shores, and seasonal changes signal the passage of time. The same forces that shaped ancient ice ages now interact with modern influences, creating a climate that is both familiar and changing. By watching carefully, measuring precisely, and studying patiently, scientists can track these movements, predicting trends while appreciating the subtlety of each component. In reflecting on the potential for future cooling, we see that natural glacial cycles are slow and deliberate, shaped by forces that unfold over thousands of years. Human activity has altered the immediate trajectory, but the system remains dynamic. Ice sheets still grow and melt in response to temperature. Oceans continue to circulate, and feedbacks operate quietly but consistently. Observing these patterns allows us to place human influence in context, understanding both its power and its limits. Even as the near-term future is shaped by warming, the Earth remains capable of large-scale transformation over time, a reminder of its enduring cycles and the continuity of natural processes. The interplay between past, present, and future provides perspective. The last ice age ended gradually, leaving a world ready for human civilization. Today, we live in a warmer period, with the possibility of future ice ages delayed by our own activity. This does not mean the planet is unstable. Rather, it shows the adaptability and responsiveness of the climate system. Ice, ocean, air, and land interact in a complex web, each responding to changes in energy, greenhouse gases, and circulation. By observing and understanding these interactions, we gain insight into the rhythms that govern our environment, from the Arctic to the tropics, from the mountains to the deep ocean. Even as we consider warming, melting ice, and changing currents, it is possible to observe the world with calmness. Snow reflects sunlight in quiet forests. Glaciers move imperceptibly down valleys, and oceans carry warmth to distant shores. The planet continues its cycles, unhurried and precise. Clouds drift across the sky, wind moves across plains, and the day slowly becomes night. Observing these processes reminds us that climate, like the passage of time, is continuous, measurable, and enduring. The shifts we witness are part of a long, ongoing story that has unfolded over millennia and will continue into the distant future. By focusing on scientific understanding and measured observation, we can appreciate the complexity and resilience of Earth's climate. Ice ages, warming periods, ocean currents, and atmospheric changes form a continuous flow, each influencing the next. Human activity now shapes a significant part of this story, but natural processes continue to operate quietly and steadily. Measuring temperature, ice, greenhouse gases, and currents allows us to understand trends, anticipate changes, and place current events in the context of Earth's history. The perspective that emerges is one of calm observation, where science guides understanding and knowledge reassures us of the continuity of planetary processes. As the Earth turns, seasons pass, and ice and snow wax and wane. Rivers flow, oceans ripple, and the wind moves across the continents. Glaciers advance and retreat in slow, patient rhythms. Ice ages come and go over millennia, leaving evidence in the land, the sea, and the atmosphere. Even now, the climate continues to change, influenced by both natural cycles and human activity. Yet the system persists, adapting, redistributing heat, and maintaining a dynamic balance. Observing these processes with care allows us to witness the ongoing story of our planet in a calm, thoughtful way. Finally, as we reflect on the long history of ice ages, current warming, and the potential for future changes, it is possible to rest in the quiet knowledge that Earth continues its cycles. Ice melts and forms, oceans carry warmth, and the atmosphere moves steadily, shaping climate in predictable and measurable ways. The planet is dynamic, resilient, and interconnected. Each moment, each season, is part of a long continuum of natural processes. Even with human influence, the Earth's systems persist, quietly adjusting, balancing, and responding to forces both ancient and modern. In this understanding, there is calmness. The world continues its rhythm, a gentle, continuous flow that we can observe with care, awareness, and quiet reassurance.